Yeah.
Short questions are easy to repeat, and then we'll pass this around for
Yeah,
later.
okay. And I'll try to keep focused on the screen rather than pointing.
Okay. Welcome back.
So Richard, is it 40 and 40? What's the time? 40 each. 40 each, yeah. Okay, yeah. If I run over, just give me a sign.
Check.
Yeah.
How many computer scientists does it take to make a microphone work? Okay, so welcome back. As many of you may have gathered from working on homework 1, it's kind of hard to tell why your program is running slower than you think it ought to. And so the good news, there are a lot of there are apps for that. There are ways to fix it. And so we have 2 talks today on that. One by David Skinner, who works at Lawrence Berkeley National Lab and is responsible, he's officially the strategic partnership lead, and he's responsible for building a number of the tools that people use to do performance monitoring up there. And about half the time he'll speak, and the other half will be Richard Gerber, who's also responsible for some of those tools up there, and he's a senior science advisor and the user services group lead to tell you about the tools that you'll need for understanding parallel performance. So, David.
Thank you, Jim. So welcome. Yeah, as Jim pointed out, Richard and I work at Scientific Computing Center, NERSC, that many of you are familiar with, and we'll be talking about really kind of tales from the trenches in some ways. We're long past studying kind of computer science as an academic enterprise, and many decades into sort of working on codes that are out there in the wild and making them run fast. So a lot of our perspective here is sort of applied tips and techniques from computer centers as they are right now. Keep that in mind if you're a young person on a mission to make a new computer language or make computers work differently. A lot of what we're going to be talking about is sort of how parallel computers are implemented right now, and how to get speed from those as much as we can. The lecture is kind of in 2 parts. There's generalities and principles that I'll be talking about, some concepts in performance analysis, some of the things that Richard and I do when people have codes that they bring to us, and we're more often involved in making the codes run fast after they were written than we are in writing them from the ground up. So a lot of what you'll see is a lot like what happens in a hospital. The patient comes in and something's sick, and we use our diagnostics to try to figure out what's going on and try to figure out the best that we can do. A lot of these tools are just that. They're diagnostics to try to help you figure out where performance is going, where time is being spent in codes. And as we'll see, very often that can be radically different from how you might conceptualize where you think the performance bottlenecks are in codes. And so it's a nice, empirical, abstract, mashup to be able to say, where do I think my code is going, and what does the tool think is going? And by putting those together, you can oftentimes make things run really fast. The generalities I'll go over in the next half hour or so, and then we have lots of details about specific software tools that you can find on Hopper or Edison. People already have accounts on NERSC at this point? Yes, good, okay. And really this is targeted, at the person who sort of was maybe like I was when I was in grad school. I had to write a code, I needed a parallel computer to make it run fast, and so the budding simulation scientist who is also an application developer, that's one of the targets here. if you're writing a compiler, middleware, kind of inventing new ways for computers to work, please don't feel constrained by what we're going to talk about. I'm sure there are lots of new tools that you could come out and revolutionize the field with. So about NERSC, we're Department of Energy Scientific Computing Center. We have a lot of users, a lot of breadth of science. We're not topically focused around one specific area overall, but Lawrence Berkeley Lab topics, energy, environment, applied math, those are the threads that run through a lot of this. And we have a very end-user focus. That is that we work with a lot of science teams that have fairly pressing science needs, that they need their code to run fast tomorrow, and we focus on that sort of work. We also spend some time sort of thinking about the future, and every 3 or so years we put in a new big parallel computer, and to do that we're interested in taking in requirements and feedback and information from those science teams to figure out what the next type of architecture is. So that's NERSC in a nutshell. What I'd like to do next is give you some big picture concepts of performance and scalability as it's found at NERSC. And one of the most important things that I'd like to try to get across is that performance is not just a single number. In a lot of papers and other places that people talk about performance, performance is talked about as a flop rate or some other sort of metric that's relatively simplified overall. If the goal is to use a computer to solve a scientific problem, then there are actually a lot of ways that performance can creep into that. And this is just some of these in terms of performance is how fast the code runs, but it's also how long you spend coding. How long do you spend marshaling jobs through the machine? How long you spend waiting in a queue? And how long you maybe spend working up your data. So there's not necessarily one number out there that everybody agrees upon about what performance means. So try to tailor it to your goals. Plan where to put your effort. A mistake that I made as a grad student was I tried to optimize the whole code. I thought I'd make the whole thing run fast, and nobody told me about Amdahl's law, in College of Chemistry where I was, and so I made that mistake on my own. But you need not make everything run fast in order to achieve a kind of fast overall workflow. The algorithm that you choose to implement, if you go out and you look at a catalog of algorithms for an FFT or a sparse solver or whatever, it's kind of like shopping for a car. There's a wide variety of options, and the fastest one may not necessarily be the one that is the best fit for your workflow. Sometimes, especially when you're getting started, trying an n-squared algorithm to see how it goes and to see whether or not n is sufficiently small that you can get by with that, it can be a very, very educational exercise. So just to wrap this up, that overall performance is relative to your goals, the time you spend in the queue, the time spent executing the code, your overall plan, and the suggestion that I have is try to focus on specific use cases as opposed to making everything perform well, at least maybe for your first couple passes through. So getting into the taxonomy of HPC performance, one simple way to break this out is in terms of serial and parallel opportunities to achieve faster performance. Chips do a lot more things than one instruction in a cycle. So the instruction level parallelism that you can find really provides kind of a benchmark for what you can do with that particular core. So if you know that you can potentially get 4 flops per cycle, and flops are what you're after, then paying attention to the instruction level parallelism makes a lot of sense. Architectures nowadays are really all about speeds and feeds and moving pipelines and avoiding using pipelines when you can. There's a very hierarchical, a deep hierarchy to how data is stored within computers nowadays, and in general, locality is your friend. That's all in a node. Between nodes, trying to find decompositions of things into tasks that can spend some time making progress independently and that communicate when they need to is important. I'll talk about latency and bandwidth a little bit in some applied ways here, but maybe just to kind of start that off, at least from my perspective, a kind of grounding thing about latency and bandwidth is that latency is really a number that has to do with the physics of the computer, about how quickly can you get from point A to point B, and bandwidth is really about resourcing, how many things can you afford to move overall, and whether a code is latency bound or bandwidth bound, that's one of the things that potentially a tool can tell you. It may not be the first thing that it tells you, but that's in the class of measurements and diagnostics that you can get from a tool. So in this, here's my version of this hierarchy here, with registers that are very, very fast, where instructions happen at the top. The sort of data concepts that go along with these, are then lines of cache that move in and out, larger pages of memory that move in and out, messages that are communicated between more or less independent execution units, and then lastly how bulk data is managed, coming into a code or being written out of a simulation. So in this hierarchy overall, these data structures are things that tools will talk about too. So who here has heard of first touch? Okay, so yeah, a few people. So the unit of data or the unit of code that you're often asked to think about from a tool has this sort of hierarchical vocabulary often in it about what are my pages? Well, they're not data structures that you probably coded into your code, but you may need to know that you need to touch those pages in order to kind of set where they are in the locality, to set their location. So the way I ask people to remember this is think globally, compute locally. There's a lot to consider in parallel computing, but there are guiding principles of locality that can really help you concentrate your effort where it matters. So now let's talk about tools. There's a strong tool culture in high-performance computing about debuggers and tools that are specific to specific machines. There are people who don't like tools so much because they tend to be focused around individual architectures. There are people who pine about the good tools that used to be that are no longer there, and all kinds of things. So let's dive in and see what these tools are about. Mapping the tool hierarchy onto the data locality hierarchy that I was talking about earlier, this is kind of a spectrum of tools of different sorts that give you information about these different kind of levels. And I've broken them out in terms of what I would call low-level tools, oftentimes libraries. Printf is maybe one of the lowest level tools that you have. PAPI is the performance API. This is something that can give you on-chip counters about flop rates, cache misses, a lot of very accounting level information about what happens on a chip. Valgrind is a tool that's well known outside of high performance computing as well that can tell you kind of how you're using your local memory resources. The name-shifted PMPI interface is a way of wrapping messaging that happens between tasks in a way that, so in addition to sending a message, you also collect some performance information about that message. So if you have a concern about slow messages overall, you could jump into PMPI and you could learn all about your messages, every single one of them if you wanted to. And on the last level is, system accounting type of utilities that can tell you about how much data are you pushing through the file system. So just outside this sort of very bare bones set of tools are higher level tools that try to insulate, some of the complexity of this hierarchy and provide a single dashboard, really, to what's going on with the code. And Richard is going to give you a very useful rundown on how to get started with some of these tools on NERSC machines in a little bit. But I wanted to first kind of lay out this hierarchy again to get across some of the general principles of performance tools. So how do tools work? Maybe you don't care. Maybe you just, you want a high-level tool, you want to follow the instructions, run it, and get your number. That's fine. In some cases, it is useful to kind of think about how you're getting that number, particularly if you want to, base decisions on it. And generally speaking, there are two broad classes of profiling codes. One is sampling, where you periodically, based on an overflow or other means, you look at the code and you build up a statistical profile of the n times that I looked at this code, what was it doing, and then you build up a statistical basis of trying to understand where time is being spent in the code. Tracing and instrumentation are a little bit more invasive. These are things that either through library tricks or through recompilation, put new code into your code to trace individual calls. And a lot of these use hardware event counters. These are pieces of hardware that are built into chips that allow introspection about resource utilization and performance. The kind of inside perspective on this to maybe help you not get as frustrated once you recognize that these are not really all that clear sometimes, is that they're by and large built for the people architecting the chip. They're, with rare exception, or there is real thought put into making hardware performance counters useful to you or to me. And so some of these APIs, like the PAPI, the performance API, are really nice because they mediate that discrepancy, and they provide more or less meaningful information from a set of on-chip resources that are kind of flaky and questionable in some ways. And in that process of mediation, one of the things that can happen is you can learn that you're let's see, is this on there? No. So on the last bullet, it says only a few, approximately 4 counters. So there's hardware performance counters all over the die, or a lot of places on the die, but you're probably in a pretty good spot if you can measure about 4 things in a given run. And that's just because, as I said, those counters are not really designed for end use in a lot of cases. And so there's ways that you can try to sample and read more than one counter, but if you want to reliably get a count on a code, you're probably not going to get about more than 4 counters per run. And one of the things that NERSC does is we try to point out that, gee, wouldn't it be nice if we could measure 24 or 100 counters per run and get hardware and software vendors to implement those ideas. So when you pick up a tool to use it, a tool may ask you to modify your code directly, or it may implicitly sort of recompile or transform your code. Then in most of the cases that we'll talk about that are not kind of static analysis techniques, we'll need to really run the new binary, and then we get a log file out. So if you've ever used gprof or things like that, it's the same sort of general approach. So at NERSC you'll find CRAPAT, which we'll hear more about in a little while. Well, there are also community tools, Tau, PAPI, gprof that I just mentioned. Integrated performance monitoring is one that's sort of NERSC specific. It's used at a few other sites, but we have, as I mentioned, a large number of users, and many of our users need some way to very quickly sort of get to what their performance assessment for their code is, very quickly find bottlenecks. And so IPM is sort of one of these dashboard approaches that tries to get you answers quickly. So what will you get out of this? If you think of your application as a stack of software, that has maybe some C or Fortran and libraries mixed into it on up, oftentimes the performance assessment that you would get is sort of decomposed in those same sorts of ways. And getting the flop count, how much memory is used, is very important. Figuring out which of the software libraries or messaging libraries that you're using, figuring out how well you're using those is really important too. So if you, for instance, find out that you're spending a whole lot of time in OpenMP and you don't really need OpenMP in your code, then that's probably a good indication to pay some attention to that layer of the stack. The types of things in MPI, that are often part of performance debugging is looking at, the overall time spent communicating, looking at load imbalance and message sizes. So I think I have one more slide on tools, and then really the generalities that I'll get into are some war stories and some worked examples in these sorts of areas. There's no one right tool for the job. Find something that works for you and run with it. If you're in computing for the long haul, you may want to consider tools that you can learn that you'll be able to reuse, and techniques that you can learn that you'll be able to reuse across architectures. And tools can add overhead too. So, for instance, if you have a newly developed code that you're wanting to get an assessment on, you might be able to tolerate quite a bit of overhead to understand the performance of the code. If you're well past that point, and now that you have to run 1,000 simulations, each is going to be 8 hours or something like that, amortizing that overhead over all those runs may be quite a lot. So building a strategy where you can assess performance in a non-production environment and then spin off a bunch of high-performance runs can be really useful. Just a little bit about IPM here. The approach that we've taken at NERSC is that knowing what's going on with hardware counters, MPI, and I/O are the three big things that our users have performance bottlenecks around in many cases. There's always much trickier cases too. So with IPM, we ask people to do a module load IPM. On the Cray machines, you need to recompile. And then this IPM linked library, when it runs, will generate some output that looks like this, that says, when this run completed, I know when it started, I know when it stopped, I know how many tasks it ran on, what the wall clock time was, what the memory high watermark was, some more information along those lines. A more detailed report can be generated that has more numbers on time spent in system time, the whole array of hardware performance counters that are out, that are available, and then at the end, an inventory of which MPI calls was time spent in. So let's see. So a laser pointer is probably not a good idea because won't be filmed.
That's right.
Okay. So in this case, if you look down at the bottom, you can see calls like MPI send, MPI wait, MPI I receive, MPI barrier. If an appreciable amount of the wall clock time is spent communicating, and particularly in a type of communication that's not making progress by actually moving data, then that's one of your first indications that load imbalance or some other sort of synchronous bottleneck to progress is there. So developing a repertoire to deal with performance issues that come up in codes can be really useful. I already mentioned about seeking portable solutions. These are things that if you are involved in computing for a long period of time, will really change quite quickly. Every 3 years, NERSC puts in a new large computer. The software stack and tools don't change radically every 3 years, but there is a lot of churn in the tool space, and it tends to follow architecture shifts. Yes. Oh, and I'm not against printf, so yeah. Okay, so that's some generalities, and hopefully that's useful to you. Really, where I think people begin to learn about performance analysis of applications is by working examples. So the kind of definitions that we need to be able to get into these, the most important ones are strong and weak scaling. So just very briefly, we have two types of extents. When we think of a lot of the calculations that people run is how big is the problem and how big is the computer. And by how big is the computer, how many, what's the number of concurrent nodes or cores that we're using. And how big is the problem is essentially, if you think in partial differential equations, a matter of how big is the grid, how fine is the grid, how many data points do I have. And so for strong scaling, we know the problem that we want to solve. There's no ambiguity about that. The problem size is fixed. The question is, what size of computer best solves that size of problem? And in a weak scaling scenario, there's more flexibility. We might be able to, for instance, do a better problem as we get more computer. So the problem that you might run on 1,000 cores might be different than the problem that you would run if you had 1,000,000 cores, because you would actually prefer to solve a larger problem. And in these two different scaling regimes, it's important to keep in mind what we mean by progress, really. And so speeding things up is progress overall. One way to systematize that is looking at the serial time divided by the parallel time. So the speed up on n cores, being the time spent on to run the problem on one core divided by the problem on n cores. And if we look at the efficiency, well, that's approximately the same thing, but divided by the total number of cores that we used. So driving down or driving speed upward only typically makes sense when the number of cores that you're using to do that is sort of efficiently used. And so that's what this type of efficiency means. And there are other definitions of these things out here. So for instance, the serial time may not be well defined. There are some problems that don't really map well onto a serial wall clock time. And so in those cases, if you're reading a paper, it's an easy thing to go check. So a good deal of performance analysis that happens at NERSC has to do with scaling studies that we're well past the part of conceptualizing the algorithm, and there is a tarball that has been written at this point, and we're interested in how do we take that existing code and make it work really well on this computer for this problem. And so scaling studies are I very much encourage people to do scaling studies, because I think it only takes one or two times really being surprised by what you thought the performance was versus where it actually goes to understand that there are lots and lots of ways to achieve really terrible performance on parallel computers. It's sort of it only takes one core out there to slow things down in a lot of cases. So do a few scaling studies and learn your own surprises about these things. But the first one that I'd like to talk about is just a large 3D FFT, and I'll give kind of a motivating example for why might one want to do this. But in any scaling study, the crux of it is really looking at the problem across either problem scales or concurrencies. So this is the y-axis is megaflops per second, and this is on 1024 CPUs. And so up is better, that's a higher megaflop rate. And the scaling study is a weak scaling study here. We're increasing the problem size, and that's the x-axis. So 100 by 100 by 100 versus 1,000 by 1,000 by 1,000 3D FFT on 1024 CPUs. So that's, and if there were more dots here, you would see that there are about 5 points in this line, and we can see by adding more computer, we get more performance. So that all looks very, very nice. So this is the same data. Yes?
Sorry, in weak scaling, aren't you also increasing the number of machines or the machine resources? So in this graph, if you keep the machines the same, 1024, is that still weak scaling if you change the problem size?
Well, strong scaling, means that the problem size is fixed.
Yeah.
Weak scaling is everything else.
Okay.
And so.
So you don't need to also increase the resources to have it be called weak scaling?
Not by my book. Jim can correct me if I'm wrong, but yeah. So the key thing to keep in mind is strong scaling, right? And so the reason that that's a key thing to keep in mind is that sometimes you know exactly the problem that you need to solve. And if somebody says, oh, well, you could solve a bigger problem and you'd get better performance, well, that's not very interesting if that's not the problem that you want to solve. So if, you know, in the course of scientific campaigns, oftentimes things start off in a weak scaling regime where people have some flexibility about how can we do a finer grid, can we do a bigger problem, can we use a bigger computer, can we, you know, can we do those sorts of things. And that's all the weak scaling regime from my perspective. Strong scaling says the problem is the problem, and, you know, so the only knobs left are architecture, concurrency, those sorts of things.
Great, thanks.
So this scaling study looks very nice, you know, in some ways, which is that you know, it goes up as it goes over. Oh, this is the same sort of data. This is in fact the same data, looking at 1024 tasks down to 16 tasks for a variety of problem sizes. This is like the you know, the USGS map of the performance landscape. You know, as you change the problem size very slowly and you try a whole bunch of different concurrencies, you'll get, you know, you can get a wide variety of megaflop rates. And so one of the first things to recognize is that that it's not smooth. And you know, so this is an important thing about scaling studies, is that if you do 2 points to perform a scaling study and connect the line between the two, you may not be seeing the full picture. You know, in here there's you know, every color is a different set of concurrencies here from, again, 1024 to 16. But maybe most importantly is the steepest cliffs in the performance landscape, you know, are quite severe. And so you can, you know, drop in performance by a factor of 2 pretty quickly just by changing the problem size a little bit. And so that may be a surprise for some people. So you know, the interpolation that we drew before is maybe not a real accurate representation of what's going on there. So why is it so complicated? Well, you know, algorithms are computer programs, and they can do, you know, conditional you know, things like switch between, you know, how they solve a problem at this size and how they solve it at another. An FFT, for instance, can solve a problem based on the prime factorization of n. And prime numbers are not a real orderly sort of progression, so you can get big differences in performance. These are some of the other reasons here, up to and including bugs in the software. So, you know, program and run your simulations defensively. There are bugs out there, and scaling studies it's not unusual for those to be one way to show those up. I actually had one slide out of order here, which I meant to show before, which is motivating. Why would we even look at an FFT in this way? This is a slide from one of the Gordon Bell Prize winners, so people who are doing really big computational work. And for a simple kind of 3D grid, if you vary you know, the size of the grid and the concurrency, all of those have to go through this sort of step of doing a forward DFT, a transpose, solving Navier-Stokes, and then back around through this cycle. Well, you can use a tool like the ones that you'll see in the second half of this lecture to get a pie chart that looks like that. And it says, well, most of my time is going into this transpose step. Well, you know, the transpose part here is an FFT that is crucial to a lot of different codes. And the graph that I showed before that was so bumpy is basically looking at what is the performance profile as the size of that box changes and the number of the size of computer that I used to solve it on.
Just a quick comment. We
Yes.
will have a lecture on parallelizing FFT later in the semester.
Okay, yeah, and okay. So that's kind of a pathological example in a couple different ways. One, I beat it to death. You know, I did that scaling study is way beyond maybe what, you know, a lot of scaling studies would be, but it's not unusual for people to think about doing a scaling study that's like, you know, just 3 points or 2 points or something. So take a broader view. It can be smoother. It's great to see scaling studies that look like this. That is, you add concurrency in this case, number of threads on the x-axis. The wall clock time gets driven down, you know, in a great way. I'm going to speed up here a little bit. So this is the last part about scaling studies, just that this is showing weak scaling. X-axis is concurrency, Y-axis is percentage of time in communication. The blue is a big, big problem. The red is a small problem, and the green is an in-between problem. And as you can see, if you do a large enough problem, oftentimes you can drive the communication down, which if you're doing computation and communication, that means your computation rate may go up. So that's one way to get performance, but you have to also ask yourself, well, what size of problem do I want to solve? And so, the route towards, high performance through extreme weak scaling may not be driving in a direction that is actually solving the problem you'd like to solve. So load imbalance is the other big thing that gets people, all the time who are coming to working on parallel computing. And so in this axis, we're looking at where is time spent in communication across 1,000 tasks. And I've sorted them from, on the far left being the tasks with the most communication time, the far right being those with the least, and you can see that they kind of break into two different categories of tasks. The coloration here is by which MPI collectives are being used, so things like all-to-all and all-reduce and barrier and broadcast. It only takes a few tasks in an MPI code and a synchronizing collective like an all-to-all or an all-reduce to really see big changes in performance. And why is that? Well, if you have an unbalanced code that's spending some time doing a synchronization step, which is red, some computing, which is green, and then some I/O, which is blue, most scientific codes are going to repeat something like that over and over again. And if they're unbalanced, then the total amount of time in red goes up because more tasks have to wait because they're, not everything is synchronized. Another example here is, output that you can get from tools that maybe you can use very quickly. One of the things that you'll find when you're using performance tools is you maybe see things that you just didn't know were there. That's sort of like if you look under a rock, that's how you figure out what's under the rock. And in this case, the second most prevalent communication call is something called MPI-COM rank for this particular code, which is not a very particularly useful call. It's just telling you which rank am I. And so my point in showing this slide is that in doing performance debugging, you can also do some real kind of sensible debugging for the code. In this case, calling MPI-COM rank incessantly probably doesn't make the code incorrect, but kind of doesn't make it a great code either. So, and the loss here is all of, 20% of the communication time is spent in this call. The last topic that I'll go over is about where performance happens and how to get information about codes through communication topology. So we looked at everything so far in terms of all the tasks are just the tasks and they're doing their thing, which may be communicating. If you look at which tasks are communicating with each other, you can build up an adjacency matrix or a graph that kind of explains where the communication is happening in the code. And these are 6 different, from the wild DOE simulation codes, some of which, you can Google any of these and read more about them. But this shows which tasks are communicating with which other tasks. So, in the case of load imbalance, we said, well, some of these tasks are different than the others in terms of how much time they're spending communicating. One of the ways to suss out how are they different or where are these different tasks coming from is to look at the embedding of the communication topology in the computing that's being done. And so that comes up by looking at, is task I communicating with task J, and if so, how much and when. So let's see how that plays out. This is I have a simple and then a slightly more complicated example. This is looking at communication topology in a simple block-structured code that's colliding supernovas together called Cactus. And in the kind of ubiquitous pie chart up there, we see we have a lot of time spent in MPI weight and some in reduce. So amongst these 256 tasks, the white bands here, those are the tasks that communicate with one another. And so if you're trying to figure out, well, who's waiting on whom and where is that MPI wait time coming from, by looking in the space of the communication ranks, sometimes you can figure out which rank in particular is maybe delayed in its communication with another. This is a striped pattern in the communication topology because it's a simple stencil. You have sort of, strides that are that you're exchanging kind of finite difference information with. This is the complete counterexample to that, which is an FFT in Paratech. It's sort of a weird truncated in k-space FFT, but as you can see, the communication topology is all lit up. There's a lot of communication between tasks across the board. And so yeah, the load imbalance and communication volume and scalar performance are some of the main three topics that I wanted to highlight in terms of generalities about performance. Let me just spend the last minute or so here wrapping up with some things that happen outside the application. And one call here, performance in batch queue space. So, submitting a job to a batch queue is a type of messaging in a way. You're saying, hey, go run this code and then return the answer back to me. And if you only have one simulation to run, then this may not be, a very interesting space to look in. But if you have thousands or millions of jobs that you need to run, then there's the whole question about what sort of performance am I seeing in even accessing the batch queue system. And so some notes on this is that, at NERSC, if you want to optimize in batch queue space, two things that you can look at. One is, your schedule. You can make things run faster by throwing money at the problem, which is you can change the charge factor. If you can run in a low charge factor, you can get more performance out of a given allocation. If you can tolerate interruption, you can use things like scavenger queues. If you're moving data, you can downshift the concurrency to a lower concurrency batch queue to do the data motion. And another thing that really gets people a lot in terms of performance debug are constraints that are built into the queue kind of inherently. And almost all HPC systems will limit how many things you can run at once. That is, how many jobs you can run at once, how many jobs you can have queued at once. And they'll negotiate wall clock time limits in different ways that involve oftentimes signaling with a soft wall limit signal that's an instruction to your computer program that it's almost out of time, and a hard one that says, kill -9. So these are the sorts of things that if you're navigating many different batch jobs, that you may want to take these sort of performance considerations into account as well. And NERSC makes it very easy for batch jobs to submit other batch jobs, and I'm sure all of you have the know-how to see how to put that together, which is that if you need to run 1,000 things and you have some of these constraints, you can actually write a little computer program that will submit your jobs for you. And you can consider writing one that submits them optimally according to your schedule and your kind of performance needs. And this is sort of an example of some ways that you can move beyond single batch jobs on resources at NERSC. Hopper and Edison, it's very easy. You can fire off multiple parallel executions at once in one batch job and then just wait for them all to complete is one way to do it. You can also do something like this that says, hey, I have 4,000 cores available. I'm going to do some work as long as I have work left to do, and write some sort of, write your own scheduler to push jobs through the machine. And AP run, if you haven't seen it, is the Cray version of MPI run. And so in this example here, it's basically saying, I have 4,000 nodes available. I want to try to use them all. As soon as some are freed up, I'll start using them for the next thing. So those are my big picture overview on performance debugging, particularly in kind of the computing center space. Richard will come up next and talk about some specifics of tools.
Thanks, Dave.
All right, guys, so just a couple of announcements as Richard sets up. So keep in mind that today is the deadline for homework 1, so hopefully you had fun with that. Don't forget, oh man, okay, don't forget the write-up for assignment one as well. It's a two-part thing, so pictures are good, words are tolerable. Yeah. So that's due tonight, and then assignment 2 will go up shortly before or after, so you get a chance to look at that. Sure. So you have some time. It's up to you. So assignment 1, we assign teams so that everyone gets up to speed. Assignment 2, you're free to choose your own teammates. All right. Thank you.
Okay, thanks. I'm Richard Gerber. I'm at NERSC, like David is. I lead a group, user services group of consultants, and we're there to answer your questions, and sure you guys will be calling us, and we're happy to hear from you at any time. I brought, a lot of people helped me down there, and I brought Woo-Sun Yang. I want to introduce Woo-Sun here. He's the real expert on these tools and whatnot, and I recently became the group lead, so as I moved more into management, I felt I really needed to bring somebody who knew what he was talking about so he could answer some questions if we had them later. Everything? Technical difficulties. Let me know if that good? Okay, good. So here's the outline. We'll talk about a few of these things. Again, I want to, let's see if I can use the mouse. There we go. To get help at NERSC, you can send us email. You can go to our help website. There's also a phone number you can call. You can look it up online. But these are the preferred ways. So what are the takeaways that I want you to get from today? One is that tools can really help you. They can help you find performance problems in your program. It can help you debug your programs. Another thing is that in HPC, there are not a huge array of tools. There are a lot of tools. I show you there are a lot of tools, but there's not a lot that are commonly used by everybody. So you have some choices, and you should find what works for you. So we'll talk a little bit about what some of the common code problems are. David already did a lot of that. By example, I'll show very briefly how to start and use some of these tools, and they kind of all work kind of the same in principle. There are details, but in principle, they're all kind of the same. So one thing is to look at is, and I think David mentioned this already, is basically when you have a parallel program, that especially when you're running on thousands or tens of thousands or maybe millions of cores or threads in the future, is how do you debug that? One way is to look for outliers. Look for tasks or for threads that are doing something different than all the other ones, especially if you don't expect them to be doing that. And then where can you find more information? So debugging. So we've all used the word. We all know, what is a bug? Well, a bug is if your code crashes, if your code doesn't finish, it just hangs, it never does anything, gets wrong answers or inconsistent answers. And legend has it that this is the origin, at least of the popular term of the word bug, was this moth that got caught in a computer relay in 1947. True or not, I don't know. Common causes of bugs. Well, we talk about sequential or serial bugs and parallel bugs. So what might be some of the things you're looking for in a serial context is you might be trying to access memory that hasn't been initialized or hasn't been allocated properly. You might have an array that you have dimensioned, and then you're reading with an index that's outside that array. You might divide by 0. And one thing, I think I mentioned it later, but one thing you might not be aware of is that a lot of compilers, if you compile with the default flags and you divide by 0 or have some other floating point exception, it'll just happily go ahead and it won't say a word. It'll just do whatever it is it's going to do. Your code might crash, but it might not. And it might calculate happily away, maybe giving you wrong answers, and then crash 5 minutes later. So that's one thing to look at. And then if you have some variables that you declared and then didn't initialize, and you try to compute with them, who knows what's going to happen. So those are some of the common things. And in parallel, you might have unmatched sends and receives. So you might be sending to one task and the other task isn't listening to it at the right time, or you might have be blocking on one and waiting for something on the other that we'll never get there. I'll show an example there. You might be calling some collectives, but you might do it out of order. I think the MPI standard says you have to call collectives in order. So you have lots of different branches and loops, and you might might hit that case. You might have a race condition where a bunch of parallel tasks are trying to calculate something, and then maybe you want to calculate with it, but maybe they haven't all finished doing that sort of thing. And then, especially with threaded programming, it's really easy to have shared memory spaces that you might modify accidentally from one thread and then try to read it with the other thread, and that might be causing problems. So things like that. But let's concentrate on the parallel ones, because this is a parallel programming class, really. So if you have a bug, what do you want to do? You want to find it, then you want to fix it, and then you want to check it, right? So it sounds very simple. But I ran across this, and anybody that has ever tried to debug a program, I think, can recognize, can identify with this. So what does it say? It says, this is just the oddest bug I've ever seen. It wasn't happening until I found the mistake reading the source code. A Schrodin bug, he says. More than that, the bug manifests itself only after I fix the broken code. It works otherwise. Well, then the broken code is not really broken. But it is. Just look at it. The guy thinks about it for a second. He goes, oh, no, my God, stop looking at it. It's the paradox. It may rip the space-time continuum. And then he goes, what the hell is that? I guess I forgot a little debug statement. So what can you do to avoid blowing up the universe, right? Well, you can take your chances and use printf and write and perhaps cause an implosion of the entire known cosmos. But beyond that, there are other things you can do, have to do with tools and letting the compiler help you. So one thing that people don't think about a lot when they're debugging is that the compiler can be your friend. So there are flags that will do things like do runtimes bounds checking on your array accesses. They can trap on those, divide by zeros, that sort of thing. They can tell you if you're trying to dereference a null pointer. They can also check to make sure that your interfaces and your functions have the right calling sequences and parameters and that sort of thing. So that's really useful. A lot of you are probably, if you've coded a lot before, you've probably used GDB. It's out there every place, and it's relatively easy to use. It's ubiquitous. You can try doing that. Of course, it just works on one task. And then there's the parallel debuggers. And so in the high-performance computing world, the two most popular general-purpose debuggers are known as DDT, stamp out bugs, right, if you know what DDT is, and TotalView. TotalView has been around longer, but DDT has really kind of taken the lead in a lot of the space. And then there's memory debuggers like map and valgrind that let you look at the contents of memory while your code is running and see if there might be bad things going on. So here's a very simple parallel programming bug. Let's see if I can get the mouse to work. So task 0 is trying to send a message to task n-1, where n is the total number of tasks. But they're both called MPI receive, which is a blocking MPI function. So they're both waiting on each other to send them something before they send to the other. So obviously, this is never going to complete. So how could you use a tool to help you find this? So before I say that, I want to put in a plug-in for this software application called NX. Have any of you ever heard of NX? There's one, so good. So NERSC has an NX server. What NX is, it's an X Windows accelerator. So a lot of these tools are X Windows based. And who has tried to do remote X? And how painful is that? It's it can be pretty bad. If your latency is bad, X is really, really tough. So we have users all over the country and all over the world. And if somebody in France at CERN maybe is trying to do X to Berkeley, it's pretty horrible, right? So what NX does is it takes all that chat that X likes to do and compresses it into bigger chunks of data so the latency doesn't kill you so bad. So if you search the NERSC website for NX, you'll see how to install and use NX. Anyway, so to use DDT, so first you compile for debugging. So I'm assuming everybody knows what make is, but if not, you can just look at the next two lines. Is you compile and link your code with the G option, which puts symbols into the code so that the debuggers know what to do. Then you set up the parallel run environment. So you have to, at least at NERSC and many places, use qsub to talk to the batch scheduler, which gets you a reservation of nodes for you to run your job on. So it means it's interactive. So you can type this at the shell and sit there and do it. But it's actually running it's interactive batch, right? So it doesn't really make sense. But it's an interactive batch job. And the V is very important because that takes your environment variables, exports it into the parallel environment, which you need to be able to display X windows back to your machine. The next line is just a technical thing of the scheduler. It just puts you back into the directory that you started the job from, but you need it. So then you start the DDT debugger. At NERSC, we use the module command. I don't know if that's familiar to you, or if you use NERSC, it will become very quickly. Module load DDT puts that in your path, and then you just type DDT and give it the executable name, and that'll start up the debugger. So the debugger comes up. I'm not going to go through it in detail. You can find that we have videos and lots of help on our web pages, but you get something that looks like this. So it comes up, you press the start button, which is up here, and then it runs. Now in this case, it runs until it hangs, right, because we know it's going to hang. So after a little bit, it goes and it hangs, and then I press the pause button, and I get something like this. So if I look at this window, I can see, because the 0 up there is white, that I'm looking at what's going on task 0 out of 4. I just ran 4 tasks in this case. And task 0 is at line 44, which is on that MPI receive. But if you look a little bit farther, you see down here at the bottom of the screen, if you click on the stacks window, this tells you where the 4 processes are. And one of them is at line 44. This is one. Another one is at line 47, which is, it doesn't really show up here on the projector very well, but it's highlighted. In fact, it doesn't show up on the projector at all, but it is highlighted right there. Oops. And then 2 other ones are at line 54, which is down probably at finalize or await or something like that. So with the debugger, you could then click on task 3, or I think if you even click down here, task 3 would take you to task 3 and would show you where that one was, and you can see that they're both sitting at an MPI receive, not doing anything, and then that'll help you figure out what's going on. Okay, that's great with the 4 tasks I just showed. You can explicitly see what each task is doing. You can understand what's going on. So, but what about when you're running 100,000 tasks or something like that? Can you look at everyone in detail? Could you even fit everyone on your screen in some meaningful way? It's tough, right? So make use of statistics and summaries. So NERSC has kind of been beating this drum for a long time. And we've done a lot. We think we've actually done a lot to push the people that make debuggers to have some kind of scalable architecture for their software. And they're starting to do that. But as I said, look for tasks that are doing something different. So if you can find some way to see things that are doing something anomalous, like maybe one task is using a lot more memory than another one, or one has done a lot more floating point calculations than all the rest, whereas you thought every task was supposed to be doing the same thing. That can be a hint. Maybe one is making a number of MPI calls, like maybe one called a collective 5 times, everyone's supposed to call it once, or something like that, or maybe one didn't call it at all. You can look for things like that. So when I said the vendors are starting to listen, if you look in DDT, one thing you can do is you can pause and look at an individual variable, and on the left-hand side, you're looking at an individual variable, and it shows it to you, the value across all the tasks. There you go. But it also shows you some statistics on that variable. So maybe that's useful. Maybe it's not to you. I think what's even more useful is shown on the right, which now I've gone to a single MPI task, and I'm looking at all the variables local to that task and what it's telling you. So it gives you the values of things like count is 1, heads, this little program just randomly flips a coin on a bunch of processors. It tells you the value of heads on this one is some 999 something, and various other things. But what's kind of cool is that now, who knows what a sparkline is? Anybody know? David knows. I know David knows what a sparkline is. So a sparkline is like a little tiny compressed graph that you can see information. You can't see the details of every one, but these sparklines are plots of the values of these variables across all the 1,000 different tasks, or however many I had, right? So you can see, for instance, this one, which is the value, the rank. So there's 100 tasks, I guess, here. So this is the rank from calling MPI rank. And so it should go from 0 to 99. And you can see that it does. So that's good. That makes sense. That line shows you that as you march across the task number, it goes up by 1. So that's cool. So as I said, this thing calls a random number to flip a coin. So this is the value of that random number on this processor, which is 0.24999. But you can see if you look across 100 processors, it's dense. It's like the value's all over the place. So that's good too, right? So that's good. If that random number was, a constant line at one value, and that was supposed to be a random number on each processor, I'd know that I'd done something wrong, right? So there's a lot of information actually in something like this. So this is great. So Woo-Sun made this slide for a recent training we had, and his whole talk is on the NERSC website actually. So take a look if you can. But the debuggers we have on the NERSC machines right now are DDT and TotalView. We have both of those. And then there's some specialized debuggers, one called STAT, one called ATP, one called CCDB. And I'll have a slide on each of these coming up. And then Valgrind, some of you may know, is a pretty well-known memory debugger. And there's a link. We have a page. If you go to that link, there's a page for this class. And it's really for David and my talk. But there's some tools and debugging links and things like that there, so you can check it out. So STAT is short for Stat Trace Analysis Tool. So you might want to try this. So STAT gathers the stack backtraces into one and lets you look at it as a call tree. So this is something you should look at and play with. I don't have a lot of experience with this. Woo-Sun's used it quite a bit, and I think he finds it relatively useful in some cases. It definitely can be. It works for MPI, CoRay, Fortran, and UPC, but not for OpenMP. So that's something the tool makers need to get going with a bit, is more thread support for some of these tools. So here's a screenshot from STAT. So the application is hung. So this is post-mortem, Woo-Sun, that it does this? Oh, this is live. Okay, so this is so it attaches to a live program. So it attaches to a live program that's hung, and in this case, it tells you where the different tasks are. So the rank 0 is over there in your function. It gives you the name of the source code file and the line number that it's on. So rank 3 is somewhere else, and then ranks 1 and 2 are there. So that's another way that you can go try to figure out where your code is hanging. So that can be very useful. ATP stands for abnormal termination processing. So this is post-mortem, right? Presumably, and it does something similar. And again, go and look out on our website. I'm not going to really have a slide on that one, but the module's loaded by default on our Cray systems, but it's not. You have to set this environment variable to actually enable it to work. And then there's something new that is potentially interesting, I think. It's called the Cray Comparative Debugger. So the idea here is that you have a working version of a code, you make some change, and then it's not a correct working version of the code anymore, right? So how many people does this happen to? Well, of course, everybody, right? So the idea is that you have a tool that you can take a working version, which hopefully you've saved, and the not working version, and go through them side by side, line by line if you want, or you can look at certain variables and this sort of thing, and help you find where the new version has gone wrong. And here's an example of what the screen looks like. As you can see, you have one up, you have the other one up, and you can do things like run to a breakpoint, and then there are expressions you can write. I'm not going to show that, but Woo-Sun could help you with that, and also his presentation has more details on our NERSC website, and alerts you when things are going wrong in one relative to the other one. So this is new. I don't think many people have used it much, but give it a try if you think this is going to help you. And then Valgrind is the memory debugging tool suite. So there's little programs inside it called memcheck, cachegrind, cogrind. Again, go to our website, and even if you have a program that you think is working perfectly and you're absolutely 100% sure everything is perfect in it because you wrote it and you know what's going on, run it through Valgrind and you'll be surprised. I've had many little programs I thought, this is just rock solid perfect. Every line makes total sense. And then you run through it and something it doesn't like, right? There's something it sees you didn't do this, you didn't do that. Sometimes it has to do with opening. It'll tell you stuff about opening files, closing files, and that sort of thing. So Valgrind is a great thing to try. Okay, so that's it for debuggers. Now we'll talk a little bit about performance and optimization tools. So the performance question really is always, I've got a program, it's running, is it running well? And how do I know if it's running well? And if somehow it isn't running well, what do I do about it? So there's no single answer. I think David pointed this out pretty well, but it's worth reiterating, is you can say, does it scale well? Is the MPI time too high? Well, what's too high? 20% of time communicating and not calculating is pretty high. You may not want that. How about I/O? We have to do lots of I/O. Everybody knows about big data these days. How much time do I want to spend doing I/O? Is 10% too high, too low? So these numbers are kind of pulled out of experience and what people seem to tolerate in their codes in general for these values. But there's no right or wrong answer. If all you have to do is I/O, then 99% of your time might be I/O. Is it load balanced? Is one task spending a lot of time doing something and all the other ones waiting? If it's GPU code or any other accelerator code, the question, don't ask yourself the question, how much faster is my GPU code on this whole GPU compared to one core on this x86 machine? You should be saying, is my GPU code faster than 2 processors? And if you have 12-core processors, you need to be comparing the GPU performance against 24 cores on an x86 processor, because a GPU is about the same cost and power consumption as one of those 12-core Intel cores or AMD cores. So those are the kind of questions to ask yourself when you say, is it performing well? So it's complicated. And then there's the theoretical performance and the real-world performance. And in a really real-world application, highly parallel environment, if you're getting 10% of x86 performance, a lot of times that's pretty good, right? Especially if you're not just doing dense linear algebra over and over and over again. And what about on GPUs and Xeon Phis? Maybe 1%. Maybe it's more. Some applications do really well. Some do really poorly. But that's your challenge. That's what you all are going to be expected to figure out in the next few years, is how to do that. So what can we do about it? Again, David mentioned some of this. You always want to, whenever you have communication, there's always latency, and you always want to minimize the latency as much as you can. So if you can aggregate messages that you have to send or aggregate data movements into bigger chunks, you always want to do that. You want to do as much work as you can before sending communication to somebody else. You want to, as you get more and more parallel concurrency now, and you get all these memory hierarchies, you're paying bigger and bigger penalties for moving this memory around. So it used to be that optimization was just about getting performance and getting more numbers calculated per second. That was all anybody really cared about. Now, your bottlenecks are often moving data around. So now you'll hear people saying flops are free. So it might be cheaper and faster to recalculate numbers rather than communicate the values of some computation to some other process or processor. You always use the most local memory as you can, and take advantage of vector. We're all amused, people my age are now all amused because we grew up learning how to write vector code, right? And then the cache-based processors came along and we were supposed to throw away all of the stuff we knew about vectors. And now we're going back and dusting out our 1980 and 1990 codes that were all vector codes, because we have these vector processors on the GPUs and the Intel Phi and things like that. Use large block I/O. So again, I/O is just like moving other data. You want to aggregate into big chunks and not have to pay that latency that's even greater on disk. And then use, in parallel I/O, use a balanced strategy for I/O. So if you have too many tasks trying to write into the same file, that's bad. But if you have too many files, that's bad too. So there's an optimization that you just have to kind of play with. And how many is too many? Well, on real-world parallel file systems today, somewhere in the thousands of files is too many, because you're contending with yourself for accessing to these files and writing to them and moving data around if you get more than that. And then you also want to use enough I/O tasks in a parallel computation to get the full bandwidth of the system, to file system, whatever it is. But if you do too much, then you're contending with yourself on the network that gets to the file system. So that's another thing to think of. So maybe using one, these machines are divided up into nodes with a number of processors or cores on each node. So maybe one I/O writer per node is a good compromise in there. But again, it's something you just kind of have to play with. And as we said, it's just complicated. So you might, if this is a kind of a performance landscape, right, there might or might not be some best possible performance you could get given your code and your problem. But there's lots of places in here that are better than other places, right? So playing around is really, it's really an art. And if you're down here and maybe you get up here, that's pretty good. And then you have to ask yourself, as David said, how much work are you willing to put into it to get up here is the best one. If it takes you 5 years and 20 people working on this code to get up there, it's almost certainly not worth it to you. So how do we solve these performance problems? Again, it's tools. We talked about CRAPAT. Intel has this vTune that, do we have vTune, Woo-sun, working? We've had issues getting it working. I think it's partially installed. I don't know if any of you are familiar with vTune. There's this community tools, Tau and Pappy, which are really APIs or function calls that APIs is a good word, and gprof. And then there's these automatic tools I'll talk about more in just a minute, like IPM that David talked about. I call it automatic. It's an easy-to-use tool. And Darshan, which is an I/O profiling tool we have at NERSC. So as an example, CRAPAT. This is the optimization tool provided by Cray on their systems. So this is the one we probably suggest you start trying to use first. It's a suite of tools. But it can do a lot of different things. So it can be used for sampling and tracing, as David described. It supports everything. And the best place to actually get documentation is to read the man pages that Cray supplies on the systems. So I'll use CRAPAT as an example of kind of the process you go through on a lot of tools. So first you access the tool, so you load the module. Then you build your application. So you clean up what you've done before, and then you type make with, I think I left out the G, but you have to have the G in there. And then you make an executable. Then you instrument that executable. So there's a code, an application that you run on your binary that instruments it, and that's called pat build in this case. So pat build produces another binary called whatever your name of your code was with pat on the end. Then you run that, and that produces a report as it runs. So then you go back and you look at that report. So it produces a text report, one for each rank. And does it produce a summary report also? A text summary report, Woo-sun? I mean, a summary report. It also produces this other file called blah, 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 .app2, which is a file that you can use their apprentice tool on to get a graphical, a GUI look at the performance results. So that's kind of the standard. There's a lot of steps to go in there, so there's a bit of work that you have to do. Cray also has an easier to use tool called Perf Tools Lite. So I'd just advise you to take a look at the documentation for Perf Tools Lite. It's a little easier to use, and it'll give you some interesting things like some of the same stuff that IPM would give you that David was talking about. Okay. There's also a product called Alinea Map. So Alinea is the company that makes DDT. So this is their performance, one of their performance tools. So it's a parallel MPI profiler with a GUI, and it'll also give you things like memory usage, the MPI usage, CPU time, instructions, I/O, et cetera, that sort of thing. It's available on, we have it on Carver, I didn't know. Hopper, Edison, and Carver, and again, there's the documentation. So one thing I wanted to talk, those things you can all go to the NERSC website and read about. You can call us and ask questions about how to use them. One thing I also wanted to talk about is what I call tools for the masses. So even using the CRAPAT, as I just said, there's a lot of steps you have to go through. You have to build your code, you rebuild your code, profile it, run it, and then look at the results. Right, so it's kind of tedious. we want to see if we can find ways to make this easier for you. And the ideal would be for you to just run your code, not do anything to it, and then come back after the fact and see all these statistics about it, or all these things it did, what it did well, what it did poorly, that sort of thing. So we have some efforts in that area. We're working with vendors. Cray is helping us out. It has this product called ARU. I think they actually renamed it to something else now, but it goes out while your code is running. It collects things from the nodes that might be useful later and from your code. Alinea has something called perf report that I think basically they are trying to productize IPM, which IPM David began many years ago. So the advantage of that is Alinea's a company with money and people that they pay, and they have a vested interest in keeping up the software. And so I think it's really good that they're coming out with this. It's not quite out yet, but it's going to be out in a month or so, I think. We have IPM, of course. We have accounting logs we could look at. We have Unix resource usage we could look at. We have some system-level I/O monitoring that was working and we're trying to get back into place. And then there's user-level I/O profiling like Darshan, which I'll talk about in just a second. So right now, a lot of this information is available. It's accessed by going to the NERSC website, and if you search for completed jobs, you'll find a page that you can go to, and it'll show for every job that's finished. I think it updates every 5 or 10 minutes now. It'll show you information about that job. So you can look at this page and find things like when your job started, when it ended, and if you click on the job ID, you can find out more things about it, including automatically what the high watermark was for your code. So this is one problem that we see a lot of, is people running nodes out of memory or not understanding how much memory their codes are using, and they'll crash a node or they'll get unexpected problems of some sort or another because of it. IPM, David showed, won't go through this real quick. The one thing I will point out about this, and it kind of amuses me, is you see the AIX here. This is from, who knows what AIX is? I guess AIX is still around, right? It's the IBM flavor of Unix. This was from a machine called Seaborg, which NERSC had 5 years ago, more. But one thing that you'll notice is, David talked about hardware counters. This chip was really, this power chip was really the last one we had that gave you some reasonably useful hardware counter information, like floating point instructions completed, and I think TLB, if you all know what the TLB is, what the TLB buffer is, it would tell you TLB misses and that sort of thing. As David mentioned, the chips we have today, the IBM chips we have, had 4 counters, I think, and I think there are more than 4 floating point instructions on the chip. So just trying to use the hardware counter to read how many floating point instructions your job did is essentially impossible on those chips right now. And so that's a bit unfortunate. But things like IPM really does, it's nice to know that 27% of your time was spent communicating. If you run with IPM and you go to the NERSC website and click on your job, you'll be able to click yet again and bring up a plot like this that shows a graphical representation of the IPM data. So what this is showing, even though David doesn't like my graphical representation, each one of these boxes is an MPI task, and you can see that in this case the metric we're looking at is kind of hard to read, but this is number of floating point operations, not a rate. It's the actual number of floating point calculations each MPI task did. And you can see that MPI tasks 0, 512, 1024, 1534, or whatever, did a lot more than the other tasks. So maybe this is what you intended, but if it's not, right here you have something to look at, right? You want to know, why is this load imbalance? Why are these tasks doing so much more work than the other tasks? And actually you can see that there are a few other tasks here, and if I can read this properly, which I probably can't, but it's I think task 511 and task 1023 are doing a lot more work too. And if you look at a different metric, in this case it is MPI receive, which doesn't show up well. I seem to have lost the red altogether from this projector. In any case, this is red and green. What looks like black is actually red. And you can see a pattern. So does this pattern look like something you might expect? Does it make sense to you that every 8 ranks are doing something different than the next 8 ranks, right? If not, then maybe that gives you a hint about some place to go look in your code and see what's going on. And then I think just about finished is something we have implemented recently is user space I/O profiling. So if you go to Edison or Hopper now and build your code, then you will get this. You have to, if you know the secret words, you can make it so you don't get this. Otherwise, you will. So your job will run. If you've rebuilt it since we implemented this a few months ago, I think it was, you will get, again, the red is missing, but you will get statistics on your I/O. So for instance, this job did more reading than writing, that you can see at the top. It read about over half a gigabyte. And the next plot gives you the I/O rate that it achieved, which is there, and you can't see it at all. But here's the theoretical maximum I/O rate up here. And again, we've washed out some things, but this code took about 30% of its time doing I/O. So again, you didn't do anything but run your code and go to the website later to get this information. And also below that, if you scroll down, you'll see that it gives you a breakdown of what size transaction you made on your write. So in other words, each time you did a read or a write, how much data were you pulling out of the file or writing into the file? So if you remember, this code was doing almost all reading. And so if you look at the legend, and again, it's kind of hard to read, but this big thing here is it was reads of 0 to 10 to 100 bytes, right? So they're really small. So as we talked about earlier, doing any kind of data transfer in really small chunks like this will really perform really poorly. So if you look at this, you see that almost all your reads are in the smallest possible bin. You see the bin goes up to a gigabyte or more. That's one place to look at immediately. So you're spending 30% of your time doing I/O in this code, on this run, and you're doing all your reading in these really tiny chunks that are almost guaranteed to perform very poorly. So if there's some way you can figure out to do those reads in a way that does fewer reads, maybe more data at one time, then you will almost certainly have a more highly optimized code. So in summary, debugging in parallel and parallel code optimization can be really hard. The tools can help. Go to the NERSC web pages. There's one listed at the bottom here in particular that has a list of all the tools we have available. Check them out. Try them all. Use the ones that work for you. And there's a reason that there's not one clear winner among all these tools, because different ones are better for different cases, for different people. Be aware of some of the more common errors and best practices. Look for outliers in parallel programs, and do go to our website for more links. And call us, write us, or go to our help website with questions. And that's it.